Welcome again to this course on basics of noise and its measurement. I am Nachiketa Tiwari. I am the instructor for this course. This is a 8-week course and currently we are in the second week of it. We are covering during this week the wave equation, and in the last lecture what I had discussed was the derivation of the wave equation from three fundamental equations: the momentum equation, the continuity equation, and the equation which dictates the process which a gas undergoes, that is the gas law. So, what we are going to do today is actually develop a general solution for the wave equation and then use that solution to make certain interpretations and explain the physical meaning of this constant term which emerged in our wave equation, which is C. We had noticed in the last lecture that the value of C, this physical constant, which was defined as the square root of P times gamma divided by rho naught, the value of this particular physical constant was fairly close to the measured value of speed of sound as it propagates in air at standard room, standard pressure and temperature conditions. So, once again, what we are going to cover today is the general solution for 1D wave equation, and then try to understand the meaning of this particular general equation. Okay, so I will start by writing the wave equation once again for pressure, so that's my 1D wave equation for pressure. Now, when you look at this equation, you observe that it's a partial differential equation and it has second order partial derivatives for pressure both in time and also in space, that is x. So, that is the first feature which you observe. And then the second feature which you observe is that if you take the ratio of these second order derivatives with respect to x and with respect to time, what essentially you get is a constant, and in this case the constant is 1 over c square. So, it is a constant, and the value of this c square is gamma times pressure divided by density. So, with this understanding you try to figure out what could be a possible solution which is as general as possible, and you do some thinking and then you realize that, oh, maybe if I have a function p of xt, and if it is such that it is a function, some function f1 which depends on time and position in such a way that it does not independently depend on time alone and it does not independently depend on x alone, but rather it depends on a combination of time and position in such a way, then maybe this solution is going to work for this differential equation. And the way to figure that out is that you plug this equation back into plug this equation or this relationship, this function, back into the pressure wave equation and see whether it satisfies. So, that is what we are going to do. So, before we do that, we have to compute the derivatives of f with respect to x and t, second order derivatives with respect to second order partial derivatives with respect to x and t. So, let us do that. So, we will first compute the first order derivative with respect to x is nothing but first order derivative with respect to t minus x over c times right, excuse me, okay. So what I do is I label this thing as f prime, and then this thing is minus 1 over c. So essentially I get is minus f1 prime over c. Okay. So that's my first order derivative of f1, partial derivative with respect to x. Similarly, now I can compute its second order derivative. So it is minus 1 over c with respect, so I partially differentiate f1 prime with respect to t minus x over c multiplied by the derivative of t minus x over c with respect to x. So I get another 1 over c. Okay. So this is nothing but 1 over c square times f1 prime prime, because I am calling this as f1 prime prime. So this is my left hand side of this particular equation. Now let's calculate the right hand side of the equation. So partial of f1 with respect to t is nothing but partial of f1 with respect to t minus x over c and multiplied by partial of t minus x over c with respect to t. So that is 1. So this is nothing but f1 prime. And similarly, the second order derivative in time is del t square is nothing but f1 prime prime. Okay. So if I plug this relation and I also plug this relation back into my original wave equation, I will see that this equation is identically satisfied. It is identically satisfied. Okay. So what that tells me is f1 of t minus x over c satisfies 1D pressure wave equation. Okay. So this is one thing that we assumed. So we assumed that pressure is a function of t and x such that it is dependent not independently on t or neither independently on x, but a combination of t and x in a certain way, and this combination has to be of this way. If it follows this way, then it will satisfy it. Now, let's look at some actual solutions. So, one actual solution could be, so this is F1. So, one actual solution could be, so we'll just write down some possible solutions. One solution could be some constant, I'll call it d times t minus x over c. This is one possible value of F1. There could be infinite such values, right? And the possible value could be t minus x over c to the power of n, another possible value. As long as we have in parenthesis t minus x over c, any of these solutions is a possible solution. Now, whether it matches reality or not, that's a different question. But all these things are, all these functions are possible solutions of the pressure wave equation. Another solution could be cosine of t minus x over c, some amplitude. Okay. Another possible solution could be another amplitude e to the power of j omega t minus x over c. This is another possible solution. So, we have infinite possible solutions. The only constraint is that t and x have to come in this form, t minus x over c. Now, we will look at the physical significance of this particular class of solutions, because it is not just one solution, but it is a class of solution, and in this class the t minus x over c comes as a quote unquote package. You cannot separate them out, it comes as one block. So, this is a class of solutions. So, we will look at the physical significance. Yeah. So, this is one class of solutions which satisfies the pressure wave equation. Now, t can have any value. Let's say that I start counting t from time t is equal to 0. So, let's say I am counting at t is equal to 0. And let's say at t is equal to 0, x is also 0. Okay. So, if I am having a reference frame, I am looking at something at x is equal to 0 at the beginning of time. Then in that, at time t is equal to 0, x is equal to 0, t minus x over c will be 0. So, then the value of function will be f1 of 0. So, this will be the value of function, and this will be the pressure at x is equal to 0 and t is equal to 0. So, the value of pressure at origin at the beginning of time will be f1 of 0. Okay. So, now we will do a matrix Tx t minus x over c f1 t minus x over c. Okay. So, at the beginning of time, and also at the origin, at the beginning of time t is 0, and if I am also at that point of time at the origin, then x is 0, then t minus x over c is 0, and the value of pressure which I will record, because this is pressure. So, this will be f1 of 0. Okay. Now, let us look at, so this is what is there. Then I am looking at my watch, and then I see that 1 second has elapsed. So, then t becomes 1 second. Okay. And then I move a distance c away from the origin. If I move the distance c away from the origin, after 1 second I move a distance c away from the origin. So, in that case t minus x over c is 0, because x is equal to c, and then the value of pressure will be F1 0. So, here this is the value of pressure at origin at beginning of time, this is the value of pressure at x is equal to c after 1 second. Then after 2 seconds, let us say I move by a distance 2c, then t minus x over c is still 0, and the value of pressure after 2 seconds at a position 2c away from the origin is still 0. So, I can keep on doing this. But what this chart tells me is that whatever pressure was present at the origin at the beginning of time, that pressure moved after 1 second by a distance of c, and the same pressure moved by a distance of 2c after 2 seconds, which means that the pressure, the value of pressure is moving with a speed of c meters per second. It is moving with a speed of c meters per second, and it is moving in the positive direction, because the value of c is not negative c, but it is positive c. So, what this tells me is that if the pressure is such that it can be expressed as a function f1, and f1 depends on t minus x over c, then essentially it means that there is a pressure function which is moving at a velocity of c in the positive x direction. So, that is what, so from that we say, because of this understanding we say that c represents velocity or speed of sound. Okay. It represents speed of sound. Similarly, we can also have a solution f2, and here instead of t minus x over c, we can have a solution t plus x over c. So, this is also a possible class of solutions. Again, in this class of solutions there could be infinite numbers of possible solutions, but if the solution belongs to this category, then again C will represent, if we go through the same analysis which we did earlier, C will in this case represent again the velocity of sound, but because I have a term positive x over c in rather than negative x over c, the sound or the pressure, instead of propagating in the positive x direction, it will propagate in the negative x direction, and the propagation velocity of that pressure wave will be c meters per second. So, in both the cases f1 t minus x over c, but in both the cases f1 t minus x over c and f2 t plus x over c, for both these class of solutions, c represents the velocity of sound, and the negative sign implies that the pressure wave is traveling forward, that is in the positive x direction, and the positive sign for the second class of solution implies that the pressure wave is traveling in the negative x direction. So, that concludes my module or my lecture for today, and tomorrow we will close this journey and move on to actually the next range of topics starting next week. So, tomorrow we will again cover some 2 or 3 important concepts, and next week onwards we will start actually working on details of how to measure sound and all the associated details. So, thank you very much and look forward to seeing you tomorrow. Thank you.